Michelle, let's go to the second use case. Things get a little more interesting here. Now you're going to bring in entanglement. So entanglement, and I think you're going to use the Barrett-Koch protocol as part of this also. I know you'll talk to us more about that. For me, this use case is a great use case for carrying, for example, keys or secrets if I'm looking to provide a physics-based, unhackable encryption methodology into my communications network. And maybe I have a classical communications network that uses RSA for public key exchange. I'm going to replace that public key exchange with an entanglement-based secret exchange or key exchange using an entanglement-based quantum network. So talk to us a bit about this topology and architecture and how you're going to approach this, please.
All right. So as you mentioned, this second use case is gonna, we're gonna be trying to achieve elementary entanglement between Alice and Bob. And, there are different ways for achieving elementary entanglement. For example, we have a point-to-point entanglement generation. But, for the purpose of, showcasing the usefulness of the visualizer when developing protocols, we're going to be using a more complex protocol this time. We're going to be using the Barrett-Koch protocol. And then we're going to be seeing how visualization actually helps us understand what's going on when we have, more complex topologies and more complex, simulations. So the Barrett-Koch protocol is a two-round protocol for generating elementary entanglement between two neighbor nodes. And so what we're seeing here on the screen is we have, again, Alice and Bob. They are, they have also a quantum memory, like the previous use case, but this time each of the memories hold 2 qubits. All right, and then we also have a new node on our topology that's called the swapping station or the mid station, which is essentially going to receive 1 qubit from Alice and 1 qubit from Bob. It's going to perform an operation that will ultimately provide the elementary entanglement that we're looking for to obtain between Alice and Bob. So another thing to note here in this topology is that we are connecting Alice and Bob to the mid station using fiber. So that's another thing that we're going to be simulating in our in this use case. So to understand a little bit what we're going to be expecting to see in the visualization, let's talk a little bit about how the Barrett-Koch protocol works. So, this is a 2-round protocol. So in the first round, Alice and Bob are going to achieve a local entanglement between its pairs of nodes, and then they're going to send to the mid station over the fiber 1 qubit. And then the swapping station is going to perform a Bell state measurement, and then the results of that measurement are going to be sent back to Alice and Bob as a classical message, right? And then if this first round fails, this means that the protocol needs to start over again. But if this first round is successful, then the protocol starts its second round with Alice and Bob again performing some operations to a pair of qubits, sending them back to the mid station, and then they're going to receive again a classical message from that mid station. So if this second round is successful, then we know that we have achieved entanglement between Alice and Bob. So let's go ahead and take a look at our script for this simulation.
And so again, here, as you set this up, Michelle, as a quantum network engineer who's running the simulation, doing the design, the visualization, I'd be looking at data sheets from this, midpoint swapping device and the 2 different memory devices on either side, and looking at all the specs on each of those, and there'll likely be different types of memories, either from the same vendor or from different vendors. And I'll look at parameters on that spec sheet, that data sheet, and I'll choose, based on the performance I need and the price, my budget, I'll choose the parameters that I can actually, I want to model. And then same thing again with the fiber optic cables that you show there. I'm going to need parameters for those, the profile, the characteristics of what's actually going on with those fiber optic cables. So you're taking all that and you're going to put that into this model now for this more sophisticated entanglement-based network model.
Yeah, that is exactly right. So for this example, for this simulation, we are again defining two quantum memories for Alice and Bob. And this time we're gonna be setting an idle noise model to each of the memories that has a better coherence time. So the decay rate here depends on the coherence time of our memories. So we're gonna be using a 10 millisecond coherence time for these two memories this time, all right? And then if we scroll a little bit further in our script, we're gonna find that we have defined also the two fibers we talked about. So here we are, simulating two fibers that are 5 kilometers each. And as we know, fibers experience attenuation and, therefore they experience signal loss. And we're going to be modeling this, photon loss via the attenuation coefficient for these fibers. And we're going to start with an attenuation coefficient of 20 decibels per kilometer. And then, this is the configuration that we're going to be applying to our two fibers. And then finally, up here, we have our beam splitter detector that sits in our mid-station node. So, this beam splitter detector is going to be simulating photon distinguishability. And, the way we do this is by, using this visibility parameter in the beam splitter detector that essentially tells us how indistinguishable our photons are. And in other words, it means, this is the probability that the two photons that arrive at our beam splitter are similar, in frequency, in polarization, and in the time they arrive at the beam splitter. So we're going to start with a 30% visibility for this first simulation. And we're going to see, if these parameters are ideal for the network that we're trying to build. So let's go ahead again and run our second use case and call it, Barrett Coke 1.log. Okay. So, same as before, our simulation is running. It has outputted a log file that we're going to use in the visualizer. So let's go again to our visualizer. We're going to give it a different configuration file because our network is different this time. We're going to be giving it our Barrett Coke 1.log file, and we're going to visualize the results. Okay. So we scroll down a little bit, see what happened. So we're seeing Alice, the mid-station, and Bob in our visualization. And then, as expected, we see that both nodes apply certain operations to their local qubits, and they achieve local entanglement between them. And then they both send a qubit to the mid-station over the fiber. And the mid-station receives the qubits here. We're seeing that it received the qubits, and then it is applying the Bell state measurement. And then the results from that measurement are being sent back to Alice and Bob, as we see here in this blue lines. And then here we've got a message saying that the protocol failed in the round 1, meaning that we didn't get any detections in the beam splitter detector. So we're going to have to scroll down a little bit more to understand, to see what else happened in the simulation and see if we were able to achieve end-to-end, entanglement between Alice and Bob. So let's scroll down a little bit. We see how the protocol started all over again because it failed in the first round as expected, but then we see that it fails again. And then, it starts and keeps failing, Mike. So this doesn't look too good.
Not too promising at all. Well, that's unfortunate. Are there, one of the things that looks like it is happening in the transmission, and I'm wondering, again, not being an expert here, but just looking at the visualization, if it's something having to do with the photon loss, which is really critical. It reminds me a lot of in classical networking, you'd have something called packet loss, which is due to losing too many bits along the line and not being able to get a full packet through as a result of that. In this case, the photon loss is creating qubit loss, it looks like. And I'm wondering if, we've got the parameters from the telco for the fiber optic lines that we're using. I wonder if maybe something along the lines of maybe the attenuation is too high. Maybe maybe it's being caused by crosstalk on the fiber optic cables that are in there. Or maybe something else is being transmitted over that fiber optic cable that the carrier maybe didn't realize, or maybe the way it's mounted, maybe it's above ground, maybe it's below ground, and there's some interference happening there. Is it possible for us to go back to the telco and say, hey, we ran the model, we used your numbers, your parameters, and we can't even get the network to really work at all. We're not getting the establishment here from end to end of entanglement. Can you take a look at maybe passive components, crosstalk, and repairs, and maybe where the cables are mounted? Could that be something that they would look at and then maybe come back to us with an assessment and maybe some better numbers for us?
Yes, definitely. That's the process we're going to be probably doing to actually take new parameters, because the previous parameters that we used are not too promising. So we're going to take new parameters this time, and then we're going to see if that improves our simulation. So you're right, this is likely due to the attenuation in the fiber. And actually, if we look at the attenuation coefficient that we used, 20 decibels per kilometer is actually a lot. So this might mean that the fibers, there's something wrong with the fibers, definitely. So let's